MC and MD. Right, so looking at the solution, right, so this is the matrix that you have to be getting, right? So of course 16K, 8K, and the second row is 38K, 16, 30, so 8K, 36K, and 6K. And the third row will be 6K, 36K, and 8K, and the fourth row will be 8K and this is 16K, right? Yep. So you can see that if you actually were to expand this out together, you will basically get the same equation on the right hand side. So this is what you actually determine the stiffness metric for this particular frame. Right? And you can see it already, the stiffness metric is always a square metric. Right? It cannot be 3 by 2 or 2 by 3 or 4 by 3. It has to be 4 by 4, 3 by 3 or 2 by 2. Right? So for this case, you know that the matrix actually is a 4 by 4 matrix. And whether is it symmetric? Yes, it is, because you can see that it is actually symmetric along the diagonal. Right, along the diagonal, and anything actually is actually a mirror image of the diagonal.
Which one?
Alright, questions for question 1? Okay, good. Sure, I mean, of course, this is a tutorial. It's really for you to actually ask questions as well if you are not sure about the concepts that we have discussed. Alright, so I guess it's pretty straightforward. So you have to actually go back and chart it out to make sure that you actually derive the answer for the stiffness matrix. Right, okay, so if not, then we can move on to question 2. Question 2 is also asking you to find the stiffness metric, right? And of course, question 2 is good in the sense that it already tells you, okay, what is the stiffness metric, right? It already tells you what is the stiffness metric you have to derive to show that the K is actually given in this form, and to find out what is P, right? So for question 2, so this is a frame that is actually given. It is made out of node A, B, C, and D, right? And after that, it has actually so it will have member A, B, B, C, and C, D, right? And for this case, what it has done is that you have different dimensions, right? This is AB is 2 meters, BC is 4 meters, and CD is 4 meters as well. Right, so the distance have to go in when you actually calculate the M1 and M2, right, and even the PY1 and PY2. So you will see the difference between the first question and second question is that the first question is simply you don't have any forces, right? You can see that question 1 it doesn't have any forces involved, so you only calculate the moments, right? But for this case, in question 2, you can see that actually there is a uniformly distributed load, right, acted at member B, C, right, and this uniformly distributed load is what form of loading? Is it a load on node or actually load between nodes? Okay, again, so this uniformly distributed load, right, along member BC, is it a load on nodes or is it a load between nodes? So you have to know that it actually is between nodes, right? Because this uniformly distributed load is already applied between nodes B and C, right? So when you with that sense in mind, you know that some form you need to actually apply the fixed end moments, how to actually induce already, correct? And also you know that you have to actually use the formula P equals to PA minus PF, right? So this is actually a more intensive question, right? Okay, and of course the question says that all their fractional rigidity is actually EI. It's just that the length is different, right? But you really have to actually account for the length when you calculate all the M1, M2, and PY1 and PY2. Alright, so let's move on to the solution. Right, so again, right, in terms of the solution, if you know that it is how many members, you must actually break it down into different individual members, right? Because as I said, when we go through the slope diffraction method, right, the M1, M2, PY1 and PY2, they are member equation, right? So it applies to each individual member. So that's why you have to break all the entire frame into individual members. Right, so for this case, you will have member. Right, you can name this as member. This is member AB, right? Correct? And this is member BC, and this is member CD. Alright? So for this case is something similar to your, let me see. Right, it's similar to your example in page 7 and actually in page 4 and page 7 of your lecture notes. Right? So over here, what you're trying to do is that, again, the convention, right? You need to actually think of it. So some students come to me that, why is it that I cannot actually get some negative sign over here? Alright, so you really have to account for it properly, because this is node A and this is node B, right? So where is your node 1 and node 2? So this has to be node 1 and node 2. Alright? And for member BC, this is node 1 and node 2. And for CD, this is actually node 1 and this is actually node 2. Right? So after that, you go back to apply all your M1, M2, PY1 and PY2, you should actually get all these equations. For example, for node B, right? Okay, this has to be, you need to apply the equation M2. Right, when you use equation M2, you will then be able to get this particular expression for your moment about B. Remember BA. Right? And then when for this force over here, right? Of course, this force here, it has to be, it's actually minus PY2. Correct? If you want to use the formula, so use minus PY2 minus PY2, and you actually follow the formula. Eventually, when you work it out, the force in node B, right? It will be minus 3E theta B divided by 2 plus 3E delta divided by 2. Right? Okay, then when you move on to member BC, right? Member BC, can you remember? Because if you look at the structure, the loading condition would only be, so for this case, we will assume that there's actually right. So, okay, for this case, if you look into the question, right? So let me just go back to the question again. The question says that after this loading, although there's actually this, uniformly distributed load is actually acting vertically, right? But what it does is that it only actually resulted in theta B and theta C, right? And also there's a delta in this direction. Right, it's actually in this direction. So if you can see that in terms of delta in this direction, probably you only have movement for B and C and D. Right, but for member BC, you know that your member BC will not actually move downwards. Right, so if you use that, right, you will actually have you don't need to derive any forces, because the force doesn't actually result into move downwards. Alright? Okay, let me just go back to the very first example over here, right? Right, remember? So back to this very first convention, right? The convention says that, if let's say this is your member that is actually AB, right, or 1, 2, and if you're going to have a certain deflection over here, right, theta 1, and you have certain deflection theta 2 over here, right? And your displacement, right, for this case, it has to be actually perpendicular to the member direction. Alright? So that's where you have you need to define your delta y1 and delta y2. Correct? But for this case, if you remember this diagram again, then you move to this particular example. The tutorial question. Alright? So you can see that for member BC, right? Member BC, if you remember the example, right, the very first convention, the member, if it's node AB, it has to move downwards. Then you have the delta Y1 and delta Y2, correct? But for this case, your member BC is not going to actually move downwards. Right, so basically delta is actually 0 for member BC. Right? But it's only for member AB and member CD. You have to actually orientate your original convention accordingly. Right? Remember, for member AB, right? Originally, your member is actually is 1, 2 is here, right? So what you need to do in order for you to map to AB is that you have to actually orientate your member, your convention to be vertically. Right? So this is actually node 1, this is actually node 2. Right? So with that, you will know that the displacement is actually in this direction. So there's actually delta belonging to member AB. Right? And then for CD, it's the same thing, I guess I mentioned already, right? So let me just use this. If let's say this is my original member, this is node 1, this is node 2, right? Node 1 and node 2. So I will always try to match with the lower number with the lower letter. So in order for me to use this, I actually rotate the member in this manner where node 1 is actually corresponding to member A, no, node A. Node 2 corresponding to node B. Right, that's how I actually rotate my convention member, right? So now if I want to solve for CD, right? Again, this is node 1 and this is actually node 2, right? So how do I rotate them? If I want to actually use the same, the M1, M2, P1, P2 there, right? So I have to actually rotate clockwise, correct? So follow, because this is node 1, this is node 2, right? So in order for me to match C and D, I have to rotate it in this manner. Right, so I have to rotate in this manner. So this becomes node 1 and this becomes node 2. Right, so that is convention you need to actually adopt. So by doing that, you will be able to actually now back to the solution over here, correct? And actually derive all the M1, M2 and Py1 and Py2 respectively. Right? So as I said already, for this case, right, member AB, right, so originally this is actually node 1, node 2, right, so in order to match this one, yeah, I turn it to here, so this becomes node 1 and node 2, and this one you can use the formula for M2 to calculate this angle, to calculate this moment for node B, and for this point, this is basically the Py2, right, so straight away you can just use the formula for Py2 to determine this particular component, right? But for CD, right? So this is CD. So again, I use my node 1 and node 2. For this case, now if I were to flip this manner, right? So this becomes node 1, this becomes node 2. So this becomes node 1 and node 2 respectively. So if I want to find out the moment about C, right? I have to use M1 to determine this particular component, right? And for this case, so which one should I use? Should I use Py1 or Py2 to determine this force here? Py1. But you have to use the formula Py1 because I have already flipped my member to be node 1 and node 2. Right, so if you want to actually find out the force in node C, you have to use the formula Py1. So work out the formula Py1, you will be able to actually get this particular expression. Alright, but of course, take note that what is the convention? The convention for this is C and D, right? By right, if I were to flip the member to be node 1 and node 2, right? Where is the force supposed to be pointing? Is it supposed to be pointing from right to left, right? So from right to left is actually positive, right? But now your force is actually pointing from left to right. So you really have to take care of the sign. So because by taking the convention of the sign, you will then be able to get this particular right expression. Right. So after that, of course, these two you really have to actually kind of rotate. For member AB and BC, you have to rotate the convention, right? But when you come to member BC, right? Because BC is actually basically horizontal, So you don't have to rotate at all. So if you apply the member equation straight away, this is actually node 1 and this is actually node 2. Right? And there's actually no force in member BC because this member did not actually move downwards. Alright, because this member did not move downwards, it's only the entire structure. Of course, this member would actually move laterally. I mean, you will actually move from left to the right. Correct? But for that, you have already counted the force in node B and node C respectively already in these two members. Alright, so this is the method you have to actually kind of like follow to actually work out the moments and the forces using Stokes deflection method. Alright? So after you have actually done, okay, work out all the moments M1, M2 and Py1 and Py2 for all the three members. Right? So after that, then the next step you will do is actually to form this particular matrix. Right? So of course, the question really asks you to find out whether the K is this value or not. So you have to, no choice, you really have to prove it that it actually, you will get this particular value, right? Okay, so do you know how to actually get this particular matrix? I guess it's the same thing that we followed from question 1, right? So the thing is that if you want to calculate what is actually theta B, right? Again, you would actually follow the same method that we have in question 1, right? Okay, over here, so M1, MB, MC, and MD, right? But instead of actually going through all the MA, MB, you only need to actually do all the working for, I think for MB, MC, and actually the displacement in a horizontal direction. Right, so by doing that, you would actually be able to get this particular expression. And how do you actually come up to this? Because you want to make it everything to be whole number, right? So you actually bring this 1/16 out from this particular expression, and you actually basically, this is the K matrix that you have actually obtained. And again, this K matrix is 3 by 3. It's a square matrix, and it's actually, you can see that it is symmetric along the diagonal of the matrix.
There's no need to divide it by 16.
What do you mean? No, actually, okay, you don't need to, but the thing is because it's better for you, it's easier for you to work with these whole numbers, right? So you are not actually dividing by 16. You're actually taking out the factor of 1/16 out from this matrix. Alright, so you can see that if I were to actually multiply 1/16 into 48, I get 3. Exactly, right? So you bring 1/16 multiplied by 27, you get 27/16. So instead of working with like fractions, right? When you wanted to actually work it with whole numbers, it's easier to look at it. So that's the reason why we bring out the factor 1/16.
Alright, questions? You okay? Sure? Right. So again, it's like you actually go through the practice.
First thing is that you must be able to form the matrix, right? After forming the matrix, so then the next step is actually in a way to solve the problem, right? So the next thing is, okay, let's come back to the question again. So the question says that if the theta is the displacement, right, is actually theta B, theta C plus delta, then K has to be this particular form, where you have actually shown already, and also show that P is equals to 20 minus 20 and 0. Right, so what is this P? Remember, our interest is always to find out the expression KD equals to P, right? So KD equals to P, you already found the K already, and D is already given, and what is P? Right? So how we find P now is to come back to this equation, what we say, we need to apply this P equals to PA minus PF. right? P equals to PA minus PF, right? Remember that? So where does the PF comes from? As I said, I asked in the earlier part of this question, right? What is this loading condition? This loading condition is a load between nodes, right? Once you have actually load between nodes, you know that you're going to induce what we call the fixed end moments. Right? That's where the PF actually comes in, right? So for this case, where is the uniformly distributed load? The uniformly distributed load is actually acted in member BC, right? So this is actually BC. And how do you calculate the fixed end moment? Of course, based on a formula, you need to actually know, right? It's actually a WL squared divided by 12, right? For this case, why is it that you need to actually find W? Because if you look at the questions, the question states is that what is the uniformly distributed load? Let me just go back to the question again. The question states that this is actually the symbol of uniformly distributed load, right? Correct? This is, this wavy form is the symbol for uniformly distributed load. But this value given 60 kilonewton, is this a small w or is a capital W? Alright, so you need to take note. If you're talking about a small w, it has to be per meter. Right? Uniformly distributed load usually comes in how many newton per meter. Right? But the thing is that this question in a way is tricky. It tells you 60 kilonewton already. So it's no longer Newton per meter. If you were to use this 60 straight away, put into the formula, you will not get it right. Correct? So that's the reason why over here, you know that the entire capital W is 60 kilonewton. You then have to actually find out what is the small w. So the small w is actually 15 kilonewton per meter because it's actually 4 meters. Right? So you need to determine the small w. Okay, so that everyone can see, right? So with that, you know that so you have obtained the small w, right? So from there, you can then use the FEM equation, which is small w L squared divided by 12. So from there, you will get out that, right, the fixed end moment on the left-hand side is actually 20 kilonewton. But of course, this 20 is in the counterclockwise direction, and the one on the right-hand side is 20 kilonewton meter, but it's actually in the clockwise direction. Right. So this is actually what you form your PF. So your PF is actually, alright, so actually, this is actually P. In a way, this is actually P equals to PA minus PF. Alright. So of course, over here you know that your PA is 0, and you're only left with PF. So you need to determine what is PF. So this equation is actually PF, right? So what is PF? Your PF first is that it's the moment at the left-hand side of the node, which is at node B, right? For this case, because it is in a counterclockwise direction, you have to actually take it as minus 20, right? Because our convention is that anything in the clockwise direction is positive. If it's in the anti-clockwise, it will be negative, right? So we calculate your PF. So the first one at the node B is actually minus 20. Right, and this is at node C, right? At node C, this is in the clockwise direction, that's why it is 20. Right? And for this case, right, what we are considering is the force in the horizontal direction. Right, so for the force in the horizontal direction, basically there's actually no force in the horizontal direction. That's why it is 0 over here. So this is your PF. Right, this is your PF. And if you were to bring your PF into this expression minus PF, so your P is equals to 20 minus 20 and 0.
If you don't include the 0 in the matrix, is it still correct?
Okay, if you don't include 0 in the matrix, right, it will not be that correct, because you see your stiffness matrix, what is the stiffness matrix? Your stiffness matrix is a P by 3, right now. So eventually your P matrix is only 2 by 1, you can't achieve match. Right, so your stiffness metric originally is actually...
What is your stiffness metric? Your stiffness metric is actually account for theta B, theta C, and delta. Right, so you need to account for what is the moment that is actually going to induce at node B, and what is the moment that's going to induce at node C. Right, and also you have the delta. Your delta is basically the horizontal displacement. Right, so you need to account for the force in the horizontal direction. In this case, the force in the horizontal direction is 0. Alright, so with that, you know that your P has to be a, is a 3 by 1 matrix, which is 3 rows and 1 column.
Okay, why is it 0, right? So I said already, because this 0, right, belongs to which one? It actually belongs to the delta, right? The delta is actually in what direction? The question says in the horizontal direction, right? So if it's in the horizontal direction, right, when you do the fixed end movements, is there any horizontal force that's actually induced in these two nodes? There's no horizontal force. That's why it's actually 0. Right? Okay? Of course, if the students, if you are actually kind of like sharp, you would ask that actually, by right, if you do a fixed end movement, right, there will be actually forces induced here also, right? Right, there will also be vertical forces applied. But if the question says that there's a delta in the y direction, then you go, so if it's going to be, because for this delta is actually in the delta horizontal, right, is 0. If the question says that there's also another delta that is actually in the vertical direction. So your stiffness metric will become a 4x4 matrix reading where you have another component over here. And this component, you need to actually account for the force over here that you are calculating. Right, so because for this case, the question only says that you only had theta A, theta B, and delta, which is actually in a horizontal direction. So you have to find out whether is there any horizontal forces. So for this case, there's no horizontal force. That's why the third component of this P matrix is 0. Alright? Yeah, so this is only half of it, half of the question. Alright? So after that, what did the question ask for? The question asked for alright, so after that, the question says that, so now you need to verify that D is equals to this particular value, right? And also hence show that the bending moment at ends B and C of the member BC are approximately minus 12.6 kilonewton per meter. And okay, so this one is actually, this has to be positive. Alright, so probably students, class, you have to take note, this is actually positive 15 kilonewton meter and it's not minus 15. Alright? So if you look at the solution later. Right, so how do you determine the next set? The next questions then, alright? Let's come back to here. So with that, what you do is that you already determine, so the interest is really to build this KD equals to P matrix, right? So over here, you know that your K is given by this stiffness metric, right? And D is theta B, theta C, and delta. And what is your P? Your P, you have determined it to be 20 minus 20 and 0. Right? So basically, you have actually, this is a 3 by 3 kind of like matrix formulation, right? So of course from this question, the solution states that you can actually go by Gauss elimination. Have you all learned what is Gauss elimination? I guess in your mathematics, you would have actually learned it, right? Okay, so if you want to actually, of course you go through this solution, you can actually use the Gauss elimination method. You can then solve what is your theta B, theta C, and delta. Alright, of course if you don't want to use the Gauss elimination method, right, you can of course use the second way. Alright, if you look into the one on the projection